The machines are safe, and but if you ask at the fitness desk, they'll either show you or get someone who can show you or is willing to show you how to use the machines, get started on them. Yeah. Well, that's good. Yeah. Yeah. I'm recording. Okay, I think you guys know we got a couple students here in quarantine, and then last Wednesday we had 5 cases on campus. Then Friday it was 11. Monday it was 20. So that's like doubling every 2 days. If that continues, if we're 40 today, I'd say we'll be back online by next week. So hopefully it'll start to level off. That's what I'm hoping. So which it could if it's kind of confined to just a group, but be aware of what's going on, I guess, and we'll adjust. Yeah, I don't want to go online either. So I've got one topic. I'm going to go into a little more detail than he has in the textbook, although this figure is from the textbook. So this is the last topic. Actually, I have a couple of homework problems related to this, and then I will send out a link to a practice exam that we can review on Friday for the exam on Monday. Okay. But you want to work through these homework problems. So I'm going to make this actually homework 8D. Okay, so I'll extend the deadline until next Monday at the exam time, and then I'll set it up so that you can resubmit all of homework 8. Okay, which is due today, but I'll put that note on the lecture as well. But at the end of this chapter, he has some. So this chapter has been on essentially analog to digital conversion. This step, if we want to transmit our analog signals digitally, and then ultimately via modulation. Okay, but this chapter has just been about analog to digital conversion. The next chapter is actually on digital baseband transmission, and then we'll look at digital modulation. Okay, so again, the sampling for transmitting signals digitally may or may not be necessary. If you've got a digital signal already, a file on a computer, a video, an audio, it's already in a digital format, so you don't need to do this conversion. But I want to talk about, so one of the with frequency modulation, we can modulate to different carrier frequencies and transmit multiple channels simultaneously. And that's called frequency division multiplexing. Well, with sampling, we can do something analogous. We can transmit multiple signals over a single wire or wirelessly by interleaving time samples from different signals. So it's kind of illustrated here, where they show this thing as a mechanical commutator, but it's really just, you can think of it as a rotating switch that briefly connects to each of these different lines. That's what a commutator is. It would be done electronically. Okay. But here they show in different signals, all run through anti-aliasing filters. Now, we have to, of course, sample each of these at the Nyquist rate. So, for example, if these were voice signals, that with the highest frequency of 4K, like the telephone company uses, then we'd have to sample each one of these at an 8 kilohertz rate. Okay. So if there's 8 different signals here, we actually have to be sampling, our commutator has to actually be working at a 64 kilohertz rate, right? 8 signals that we need to sample at 8 kilohertz. Okay. So you can think of this as briefly tapping into each of these. I'm going to stick with eight different signals coming in. And then, so the output here would be, samples from 8 different signals. And then we could either pulse amplitude modulate those, and I think I'll show that in the figures I draw today, or pulse code modulate those. Okay. And again, the binary rate would then be, if it's 8-bit, it would be 8 times the 64 kilohertz coming in. Okay, but it's a mixture of different signals all coming in. And so I'm going to show it. Here's what I'm going to use for a block diagram to represent the multiplexer. Now, there's typically one channel that's always 0 or always 1. It's called the marker channel. And you'll see why that's necessary when we look at next couple figures here. But here I'm going to show a multiplexer. Now, the sampling rate is the sampling rate of each of the inputs. So S1 of t, S2 of t, and then S3 of t. And so this would be a 4-channel multiplexer, 4 signals. It would be clocked at 20 kilohertz, the sampling rate for each signal times the number of signals. And you can imagine, what I'm going to show is pulse amplitude modulation, although again, typically in place of each of these pulses, you'd have an 8-bit binary code word or a 16-bit binary code word, but I'm just not going to draw out the 8 bits, okay? So you could think of this 8 bits from the marker, and then S1, and then S2. So what I'm illustrating is pulse amplitude modulation, right? Sampling at each of these different signals. And then, S3, and then it would repeat. And then we get the next sample of S1, and then the next sample of S2, and then the next sample of S3. And this would go on forever. Okay. Now, the terminology that's used here, one full set of samples is called a data frame. So one complete rotation of this mechanical commutator, that would be called a data frame. So it would consist of the n samples Again, it's just easier for me to show these, a lot less time consuming to show these using pulse amplitude modulation. And typically these days, each one of these would be converted to a binary code word and would use pulse code modulation. Now the purpose of the marker, okay, you know, we're kind of wasting a channel we could be using to send information, but it has a vital purpose. You know, when we connect to this thing at the receiver, we'll just see a long string of pulses without the marker. If it were, you know, if we called it S0 and sent a different signal there. Well, there's no indication on the individual pulses which is actually S1, which is actually S2, which is actually S3, if the marker weren't there, right? If it were another S0, you know, so I could connect my receiver right at this point and get this S2 sample next first, and, you know, maybe mistakenly assume that that's S0. So the purpose of the marker is just to provide some indication. It's usually either at the first pulse or first code word. If it's converted to a binary code word, it might be a special 16-bit pattern or 8-bit pattern that I can look for that and say, this is the start of the frame, or, you know, it's usually at either the start or the end, okay? And then so I hook up my receiver, you know, I would look for the marker. Then once I find the marker, I know then the next signal is S1, and I can route it to its appropriate destination. Okay. Any questions about that? Okay, I think I've got another picture here. This is what's called a T1 frame. So AT&T uses what's called the T carrier system for TDM. Okay, and you may have heard of a T1 line or a T2 line or a T3 line or T4. Those are commonly used for networking. This is a system that's designed to carry binary data. Okay. And in this, a T1 frame is kind of the fundamental frame. A T2 frame consists of multiple T1 frames. A T4 consists of time multiplexed T2 frames and so on and so forth. But a T1 frame consists of 8-bit samples from 24 signals plus one framing bit, which is another name for marker. And then the signals are sampled at an 8 kilohertz rate. So this is telephone audio quality. Okay, so 8 bits per sample, 8 kilohertz sampling rate. So it's sufficient for voice, you know, up to about 4 kilohertz. You know, CD quality is 44.1 kilohertz sampling rate and 16 bits per sample. So what this is showing is they're showing 1 bit here that's the frame bit that would always be present. And then here they're showing this alternating, but, you know, this would be an 8-bit pattern. Of course, the 8-bit binary value corresponding to the sample from the first signal, the first telephone conversation. You know, so it'd be a 0, 1, 0, 0, 1, whatever. So in this picture, it's showing them all. They look identical, but, you know, there'd be the corresponding 8-bit sample code words here using a some sort of return to zero line coding. And so we've got 24 samples from 24 signals, plus all at an 8 kilohertz rate, plus our framing bit. So a T1 line is capable of carrying between two endpoints 24 simultaneous voice conversations, right? So you have 24 different phone signals coming into a T1 line, okay, and then that goes to another destination, and then those would have to be split out, okay. We use a commutator to form them and put them all on one line. We'd have to decommutate at the receiver to separate them back out into the 24 different destination points, okay. So the number of bits per frame, we've got 8 bits per sample times 24 samples per frame and then plus just 1 bit per frame, which is the marker, is 193 bits per frame. So there are 193 binary bits in a T1 frame. Now the binary rate is n times 8,000, right? We've got to sample each one of these phone conversations at an 8 kilohertz rate. So we have to generate these 193 bits. We have to generate a complete frame every 8 kilohertz, okay, at an 8 kilohertz rate. So this is 1.544 megabits per second. Okay. And this is the standard sampling rate for a T1 line. It's known for 1.544 megabits per second. Now, here I'm showing a T1 frame actually used to transport 24 different voice channels, but it's used for more than that. T1 has kind of become a standard. It can be used for just transmitting digital signals. Okay. Purely digital signals, taking up all time slots. Okay. So T1 lines use a bipolar coding. It's called alternate mark inversion. And this is the bipolar format that we looked at. So if you remember, it was a 0 is a 0, and then a 1 is a high, but the next one that's transmitted is a low. So it alternates between 1 and low. So in telephony, a 1 will occasionally be referred to as a mark, and a 0 is referred to as a space, just different terminology. So alternate mark inversion means that the ones are alternately high and low, high and low. So this is the same bipolar format that we looked at last time, the same bipolar code. Okay. So they'll either use bipolar signaling or a variant known as B8ZS. And we didn't talk about, I told you we didn't cover all the possible line codes last time. We didn't talk about B8ZS. That's bipolar with 8-0 substitution is what that stands for. And I forget the details. I'd have to go back and look it up. But They do, I think it's a technique where if they have 8 zeros in a row, and remember, that would cause you to lose synchronization. You said if you had a long string of zeros or a long string of ones. So with 8 zeros, they actually, when 8 zeros occur in a row, they actually substitute in a different binary pattern. Okay, and then they look for that pattern and then resubstitute the zeros after the at reception. Okay. Now, where things get interesting and why I like these problems, and so there will be a problem related to this on that next exam, is when it often occurs in what's known as telemetry, where you're at a remote location or you have sensing equipment at a remote location that's not convenient to access, and you need to transmit data, to some other destination. Like, maybe you're monitoring temperature and pressure inside a volcano or on the moon, okay, or in Antarctica, and you've got sensor equipment there, and you don't want to have a human there that's monitoring, taking the measurements, right? Or maybe on a coral reef or something. So it's telemetry. Tele is remote measurement. So that's what this stands for. So in this telemetry problem, though, you typically, you may have different types of sensors, some that require different sampling rates. Maybe one only needs to be sampled at a 1 kilohertz rate, okay, and then another needs to be sampled at an 8 kilohertz rate. Okay, that's where this gets a little more interesting when you have these dissimilar channels, and this requires the use of submultipliers. Okay. Now, the reason I like these problems is because they really force you to have a good understanding of sampling. Okay. And they're relatively simple. Okay. Like anything else, it's simple once you understand it, I guess. But I'll work through just an example problem to illustrate. So we've got a 6-channel multiplexer, and it's sampling each channel at an 8 kilohertz rate. Okay, so it's operating off of a 48 kilohertz clock, 6 channels times 8. Okay, so design a TDM system to accommodate 6 inputs. And this seems relatively simple. You got 6 channels, you got 6 inputs, but I'm going to require that you include a marker here. So that means you've only got 5 channels for 6 inputs. So with signal bandwidth equal to 8 kilohertz, 3.5, 2.0, 1.8, 1.5, and 1.2. Well, and suddenly it became a lot more complicated because I've got a signal here that's got an 8 kilohertz bandwidth, but my multiplexer is only sampling at 8 kilohertz. Okay. The Nyquist criterion tells me I need to sample this thing at 16 kilohertz. Okay. So that's thrown another monkey wrench into the works, along with this requirement that I include a frame marker. So what we'll have to do a couple things. We have to do what's known as super commutation for the signal that requires a greater sampling rate than our base sampling rate. And then I'll also need subcommutators to combine signals together to feed into my main commutator. So what you need to do, the starting point for these problems is to make a table that consists of, for each of your signals, S1, S2, S3, we've got 6, right? 4, 5, and 6. Corresponding bandwidths for each of the signals. In some problems, you may be given the signal bandwidth, and others you may just be given the Nyquist rate, but here we were given the bandwidths. So I've got to calculate the Nyquist rates. So this is 16, this is kilohertz, this is kilohertz, 16, 7, 4, 3.6, 3.0, and then 2.4. Okay. And then the number of channels here that are occupied, I want it to be, a power of 2. Okay. Now this one, my base rate here is 8 kilohertz. So this is going to have to take up 2 channels. And I'll show you what I mean by that, how we connect that. Okay. This one, I can get into 1 channel. Okay. The 7 kilohertz sampling rate, that's fine. It'll take up 1 channel. Okay. Now, here, I can fit this into half a channel, and I'll show you what I mean by that, right? It requires 4 kilohertz. I'm sampling at 8. This I can also do at half, okay? Now, half of my sampling rate is 4 kilohertz. A quarter would be 2 kilohertz, okay? But how many channels have I used? 2, 3, 4. I've got 1 channel left because I've got to reserve 1 for my marker. So if I do this at a half and a half, my sum is 5. Okay, so I've still got room for my marker. Okay, so the actual sampling rate here would be 2 times 8 or 16. This would actually be 8. This would be 4, 4, 4, 4, right? So I'm exceeding the sampling rate. I have to show you how to connect these things up. That's the next step, but making the, and then this table will make a little more sense, I think, after we show the connections. So, but this is 5 total channels, and I've got 1 channel for the marker. Okay. So I'm going to sketch my main commutator here, and it has 6 inputs. Fs is 8 kilohertz, N is 6, so I need a 48 kilohertz clock. Okay. And then there'll be 1 signal coming out that's multiplexing all these. Okay. So I put my marker on 1. Okay. Now I need 2 channels for signal 1. Okay. And these, I don't want to use adjacent channels. I want to use actually channels that are equally spaced apart as we go around in the frame. Okay. So here, if I use, like if I call this 1, 2, 3, 4, 5, 6, if I use channels 2 and 5. So 2 will come along, I'll skip 2, and then sample at 5, and then I'll skip 2, and then I'll be back at 1. So the idea is in my frame, again, I'm showing pulse amplitude modulation. Again, although what's typically done is pulse code modulation, but I would have S1, S2, S3, S4, S5, and then my marker again, and then actually what I said, I was going to do this one S1, right? S1 is the first marker, S1, skip 2, marker, or S1, then I'd have my marker again, and then S1, okay. Notice I've got equally spaced samples of S1 here. Okay. Since my frame rate is 8 kilohertz, then the rate at which, and I've got 2 samples of S1 per frame, I'm effectively sampling S1 at a 16 kilohertz rate, right? I've got 2 samples per frame, and my frame rate is 8 kilohertz. And notice that they're equally spaced. What happened? This is my marker, right? Thought I had them equally spaced. 1, skip 2, 1, skip 2. So what I drew my picture wrong. It's 1. This was 1, 2, 3, 4, 5, 6. 1. Oh, S1 was supposed to be right here, right? At 2 and 5, right? So I just put S1 in the wrong spot. Okay. So S1, 2 samples, S1, 2 samples, S1, 2 samples, S1, 2 samples. We want to make sure that our S1 samples are equally spaced. So I'm effectively sampling at an exact 16 kilohertz rate. Is that clear? By using 3 channels, I could get effectively a 24 kilohertz sampling rate. And here I would do 1, skip 1, do this one, skip 1, and I do 2, 4, and 6, and they would be equally spaced. Okay. So this is called super commutation, where I'm actually feeding one signal in on 2 or more inputs to my multiplexer. Okay, that's called super commutation. The other thing that I need, now S2 is taking up a line all by itself, right? S2 is taking up a single channel. And then S3 through S6, they're each taking up a half a channel. So for S3 and S4, I need another commutator that's operating at a 4 kilohertz sampling rate, 2 channels, 1 and 2, S3 and S4. Then that output, I'm actually going to feed into this. Okay. So is that clear? So they're going to be sampled at a 4 kilohertz rate. I'd need an 8 kilohertz clock here. Okay, the 2 times the 4. And then I would multiplex. So this is called subcommutation. 5 and 6 also need to be sampled at a 4 kilohertz rate, creating a signal that needs to be sampled at, well, the samples would actually be coming out at an 8 kilohertz rate. Okay. And then these all need to be synchronized. So this is 8 kilohertz. But I can take my 48 kilohertz clock, divide it by 6 to get my 8 kilohertz clock, to get that synchronization. Okay, just take every 6th pulse out of my 48 kilohertz clock. So you can do that with a binary counter to generate my 8 kilohertz clock. So again, what would the frame here look like? So let me come back here to this picture since I've already drawn it. I would have S1 and then S2 and then S1, S2. But in this fourth one, I'm going to have either S3, so I'm going to mark S3 first. Okay. But then in the next frame, it would be S4. Okay. So S3 and S4 are, and then in the next frame, it would be S3. And then the frame after that would be S4. So S3 and S4 are effectively sampled at a 4 kilohertz rate. My frames are 8 kilohertz, but I'm only including a sample from S3 or S4 every other frame. And it's the same for 5 and 6. S5, and then S6. And then in the next frame, again, it would be S5. And again, I'm showing pulse amplitude modulation, but actually each of those pulses would be an 8-bit code word. Okay. Now, there is one problem here. It goes back to the reason we inserted the marker. I can I have a marker which will give me the start of the frame, but the problem is now I can find the marker, but I don't know if it's the S3, S5 frame or the what I do here, S1, S2. I messed this up again, didn't I? S1, S2, S4. This should be an S1. And then the next one, 1, 2, 3, 4, 5. And then this one would be S6. So when I find the marker and start synchronization, I can pull off my S1 and S2, no problem. But if I start here, this sample's S3, but if I start here, it's S4. Okay. So a couple different ways to do that. One is to actually alternate the marker, transmit high and low, and then find that to be able to identify between the different frames, or transmit some particular pattern using the markers. Okay. Any questions on this? Okay, so I've assigned a couple of homework problems. Again, the homework, I'm going to extend the due date. It's not due until Monday. That's when our exam is. And I'll also post up a practice exam that we'll go over on Friday. Pretty sure on the practice exam, there's a problem similar to this, as well as on this exam is the FM material, as well as the material from this chapter. So it's over, what is it, chapters 4 and 5, 5 and 6. What chapter is this? This is chapter 5, 4 and 5. Okay. But that's all I've got for today. Questions? No? Yes? No? Not yet. Okay.